Take your attendance first. Okay, class. So let's start our today's lesson. Okay, so okay. So about circular motion, the day I think I asked you to do the 3 questions. Maybe some of your friends are struggling. So those who got answers, can you post the working on the WhatsApp? Okay, those who got your answers, can you help me to, maybe you can send me personally, then I check, I post it back into the group so that it's helpful for your friends to get to know how to do the 3 questions. Okay, so hope you can do a favor for your friends, those who are able to get the working for the last 3 questions. Okay, so come to gravitation. So far we discussed about gravitational field, right? So we discussed about when Newton, how he discovered the equation F equals to gmm over r squared. He tell 3 things. When apple fall on his head, it said all masses are attractive in nature. The force is directly proportional to the product of mass. The force is inversely proportional to the square of the distance. Then after 100 years later, the constant has been found. Then, yes, that's what able to, these are the questions you can give a try, but this is from the PowerPoint actually, which already have the working in the PowerPoint. And we talk about gravitational field strength. Okay, gravitational field strength, force per unit mass. Okay, force per unit mass, gm over r squared. Okay, so we stopped here. I think the day, gm over r squared. So this is 9.81, right? The gravity last time we thought is constant 9.81, but it has a formula now. It's gm over r squared. Okay. Okay. So now we're going to discuss the day I asked you to find what are the factors affects this gravity for the Earth. Okay. So that's going to be our discussion today. Okay. So, okay, guys, can you hear me, right? What I'm talking? Anybody?
Yeah.
Okay, thanks. Okay, so I don't know, maybe some of you have gone through how these 3 factors affects. Okay, first we talk about altitude and depth. Altitude and depth affects gravity. Altitude, quite clear, because the equation gm over r squared, r is increases, that means altitude increasing, the g drops. Okay, altitude can be concluded by using the equation itself, gm over r squared. Okay, now we're going to talk about depth, but before we go to depth, altitude, effect of altitude on g. From the equation, we can show that gravity is directly proportional to the inversely proportional to the r square. So greater the r, smaller the smaller the g. So greater altitude, smaller gravity. Okay, therefore graph follows the inverse square law. It's called inverse square law. G inversely proportional to the square of the distance, called inverse square law. because the r is square. Okay, look at this graph. In exam, they will check carefully. Now, what they're going to check? At the beginning, at r, let's say the force is F. At 2r, it should drop to quarter F. They will check that. You can't simply draw a curve. You have to draw a curve such that at 2r, it become quarter F. At 3r, become how much? 1/9 F. You know, right? 4r, how much? 1/16 F, correct? It's because r squared. In r double, it become quarter. In r triple, it's become 1/9. So the graph, when you sketch, make sure the proportion, how much you should drop, you should know. They will check. Okay, so going out, gravity drops. Okay, now going in. So effect of depth. Will G approach infinity when R approaches 0? I already told you. It's going to be 0. Okay, why it's 0? Why the gravity go to center of the earth becomes 0? The reason is this. You can imagine like this. Okay, let me go to the whiteboard. Okay, let's say this is the earth. Okay, you are standing here. You are the M1. The earth is M2. So according to Newton, the M1, M2 are attracted to each other. So you are pulled down. But let's say you move to the center of the earth. Finally, you are at the center of the earth. You are at the center of the earth. You are surrounded by the mass. You are surrounded by everywhere. Everywhere you get earth mass, surrounded by mass. So according to Newton, the mass and mass, your body as a mass, the earth is surrounded by mass. So how? The earth going to pull you in which direction? The earth going to pull you in all direction. Okay, up got mass, down got mass, side got mass, left got mass. So all going to pull in all direction. So when you experience a force in all direction, okay, same force. So what is the net force you will experience? Net force. Force up same as force down, force right same as force left. Because you are surrounded by the same mass surrounding. Okay. So what happened to your net force? Net force become 0, right? Net force 0. So when net force 0, ma equals to 0. So acceleration will be 0 meter per second squared. So your a in this case is your gravity. So at the center, your gravity will become 0 because you are surrounded by mass. Okay. As I told you, like the movie, the Godzilla versus Kong. The Kong will go into the center of the earth, fall down, but when it comes to the center, it float. Okay, it start to float. So doesn't make sense, that movie, because we can't even go to the core because temperature is quite high for the sake of movie. But the floating part is correct. Center of the gravity becomes 0. Any questions, guys? Understanding? Why gravity at the center of the earth is 0? Because you are surrounded by mass. All over the place you got mass. So the force going to pull you all direction, equal magnitude. So your net force is 0. So your acceleration is 0. So gravity is 0 at the center. Any questions? Okay, maybe you can further understand through derivation. Okay, so if I go to that, yeah, so this is the derivation proving, go to the center, the gravity becomes 0. Okay, when you approach towards the center, the G goes to GM over R squared. Okay, remember another one thing. When you are, this is the Earth surface. Okay, the Earth. When you go towards the center, let's say you are somewhere here. Okay, the mass which is responsible for gravity is the mass under beneath you. And mass under beneath you, like a point mass. This is the mass responsible for your gravity. The side mass already cancels the gravity at the side, but the mass pulling you down, the mass under beneath you is the one responsible for the mass. Okay, so when you go towards the center, the mass which is responsible for your gravity becomes smaller and smaller. So that's why here the G goes to GM or R squared. The mass under beneath you, they change the mass into density times volume. Density times the volume of under beneath you. And the volume under beneath you is 4/3 pi r cube, because we assume like a sphere under beneath you. So the r cube, r squared cancel. So this is the new equation which developed to find gravity inside the planet. This equation is inside the planet. So finally, the G is found to be proportional to R. The G is found to be proportional to R inside the planet when you go towards the planet. Okay, so therefore G is directly proportional to R when go into the planet. Okay, so yeah, so this is the idea. So the gravity go to a center becomes 0. But this is only correct. We did some assumption. The assumption is the Earth must be perfect sphere and has a uniform density. The density have to be uniform everywhere. It must have the same density. Okay, so that's why when you at the center, on the right, on the left, you have the same mass, so you have the same force. So the force is balanced. So the Earth must have a uniform density for this proposal to be accepted. Okay, so yeah, so that's why they say roughly the G going to be 0 at the center. So we keep everything in mind. This is the final graph for G versus R. Okay, so inside the Earth, it's linearly proportional. And when come to the surface, the G is for the Earth is 9.8. And go out of the Earth, the G drops inverse square law. And G proportional to 1 over R squared. So it's going to drop inverse square law. Okay. And inside, G is found to be proportional to R. Now, this prediction is only correct. The Earth is spherical and homogeneous. In exam, if they ask, what is the assumption for this prediction? The Earth must be perfect sphere and homogeneous. Homogeneous means uniform density. Then only it works. Okay. The left side is the explanation I told you. Gravitational field at the center of the Earth is 0. This is because any matter at the center would be pulled equally in all directions because surrounded by mass. The Earth mass is surrounding you, so all direction the same force, giving a resultant force on the mass as 0. So you have a 0 gravity at the center of the Earth. So you'll experience weightlessness like floating in outer space. But of course, in reality, we can't go towards the center because of temperature, pressure. It's quite huge. Okay, so this is the first factor. What affects gravity? How gravity changes in depth and altitude. Okay, greater the altitude, gravity is smaller. Go to the depth, gravity is smaller. Where do you have maximum gravity? Only at the surface of the Earth. Now we are experiencing maximum gravity. At the surface of the Earth, the gravity is the maximum. Okay. Any questions? First one, anybody? No questions, eh? So in exam, not even once they asked about what is happening inside the depth, inside the inside the Earth. Always they ask how gravity change outside altitude. So outside the Earth, how the graph going to change is very important for you to remember. Okay, G is inversely proportional to R squared. R squared. Okay. Okay. So we go to the next factor. Okay. Next factor, what affects gravity? What affects gravity? Latitude. Okay. The other class, Friday, I told you the North Pole and equator. North Pole found to be as a greater gravity. Latitude affects gravity. Why? Why North Pole has a greater gravity? Okay. So why North Pole has a greater gravity? So this is the reason why North Pole has a greater gravity. This picture tells you, see, the equator, the person weighs 978 Newton, but when he goes to the North Pole, it's become 983 Newton. Okay, so you get heavier, gravity gets stronger. Why? There are two reasons. Actually, there are two reasons to explain it. The first reason is, in reality, the Earth is not spherical, but a little ellipsoidal. It's ellipsoidal, actually, our Earth, because of the rotational effect. When something rotates, the side edge will start to bulge, start to get a little elongated. It will get elongated little. So it looks like ellipsoidal. Okay. So scientists found that the equatorial radius is actually exceeds the polar radius by 21 kilometer. Okay. That means the equator radius is 21 kilometer longer than the North Pole radius. Okay. The height of the Everest mountain is how much? Around 8 kilometer plus, I think. So the extra height increment experienced by the equator is like 21 divided by 8, like 2.5 times, around roughly 2.5 times of Everest mountain height was extra at the equator. Okay, so R is greater at equator. So how this causes the change in the gravity? Okay, how this change the gravity? Of course, R different means G different, right? Okay, according to what formula? G equals to GM over R squared. Okay, G equals to GM over R squared. G equals to GM over R squared. So greater R, smaller G. So that's why equator results to a smaller gravity than the North Pole. Okay, so because of greater radius at the equator due to rotational effect. Okay, this is one reason. Okay, there is another one reason, but before I discuss about another one reason, I will discuss the rotational effect first. Any questions about latitude effect? Why latitude affects gravity? Because radius is different. Earth is little ellipsoidal, not perfect sphere. If it's a perfect sphere, still there'll be a difference because of another reason. I will teach you that after I discuss the third one. Any questions, guys, from latitude? Okay, hope you got the idea. Okay, the third factor. This is the most important factor frequently asked in exam. Okay, Cambridge really interested to check how gravity affected by the rotation of the Earth compared to the other two factors. Okay, the latitude looks like very inferior compared to rotation for Cambridge. So you really need to know in depth how rotation affects the Earth. Okay. Okay, so before we read this PowerPoint, okay, I go to the whiteboard and to help you. Okay, maybe okay. Okay, yeah. Go to the whiteboard first to explain the rotational effect. Okay, so let's say Earth. Okay, you stand here. Okay, equator, and you stand a little up here. Okay, okay. So you stand here. We are considering the Earth rotation. Earth is rotating. Earth is rotating. Earth is rotating. We are considering the Earth rotation. Yes, we never consider the Earth rotation. For this gravitational topic, we consider the Earth rotation. Okay. If you are at the equator, Earth is rotating. You are acted upon by a balanced force or unbalanced force. Earth is rotating. You are acted upon by balanced force or unbalanced force. Okay, first of all, before that, what are the force acting on you when you are at the equator? What force acting on you when you are at the equator? Anybody? What force acting on you when you are at the equator? So what force pulling you down into the center of the Earth? What force? The gravitational force. The gravitational force between the Earth and you pulls you down, the Fg. The Fg is actually the Gm over R square. It's pulling you down towards the center. What are the forces acting on you? There is one force push you up, right? What force is that? Normal reaction. Normal reaction pushes you up. Okay. So these are the two forces acting on you. Okay, now if you consider the Earth rotation, okay, if you consider the Earth rotation, you are act upon by a balanced force or unbalanced force. Janyon, yeah? Janyon, what do you think?
I don't think so.
So it's acted upon by a balanced force or unbalanced force?
Unbalanced.
Unbalanced force, good. So it acted upon by an unbalanced force. So everyone agree it should be an unbalanced force because it's rotating. So circular motion, from circular motion knowledge, anything rotates in a circular path, it definitely act upon by an unbalanced force. I told you this when I discussed the circular motion. Where the unbalanced, the net force acting, where the net force acting towards the center of the circular path. That net force is called centripetal force. Okay, right? That's centripetal force. So now tell me, for you at the side of the equator, you act upon by unbalanced force. What equals to centripetal force for your body? What is your centripetal force for your body? Okay. Anybody? Whatever force acting towards the center minus whatever force opposing should be the centripetal force, right? So in this case, what force acting toward the center of the circle? Fg. What force opposing? Fn. So what's the equation? What equals to Fc? Fg minus Fn is the centripetal force. Okay, what I'm trying to do now? Why I'm showing this all? I want to show how rotation affects gravity. Okay, how rotation affects gravity. Okay, I believe all of you understand this equation. Fg minus Fn equals to Fc. Okay. Okay, now, anyone don't understand this equation? If your circular motion you understand, you should come out with this formula. Whatever force acting towards the center minus whatever force opposing is Fc. Okay, so now I want to ask you an important question. Okay, let's say you are standing on a weighing scale at the equator now. You are standing on the weighing scale. Weighing scale means you are standing on a weighing scale, and weighing scale gives you a reading. The weighing scale gives you a reading of the weight. The reading of this weighing scale is which reading? Fg, Fn, Fc. Oh yes, this one. I want you to WhatsApp. I want to see how many of you really understand this. I give you 1 minute. Very important for you to think. You're standing on the weighing scale. Okay, the Earth is rotating. Okay, Fg acting down, Fn is acting up. Fg minus Fn is centripetal force. When you stand on the weighing scale, the reading portrayed on the weighing scale is which reading? Fg, Fn, or Fc? Okay, guys, the others come on, give a try. What do you think? Okay, one of you said Fn, normal force. The others, I give you 1 minute for you to think. Real, okay, so yeah, two of you said normal force. Your class is good, So all of you said normal force, Okay, good. So I'm happy. Yes, it's a normal force. The force which will be the value which will be stated on the weighing scale is your normal force. Okay, the normal force is the one stated on the weighing scale. Okay, so this normal force for this case we call a special name. Okay, I don't know whether you heard of that name. It's called, this is your apparent weight. This is your apparent weight. Apparent weight means the weight we are experiencing. Okay, so if it shows 800 Newton, so we equate equals to mg, we find gravity. So 800 Newton divided by your mass, you get gravity. So the gravity has been calculated through Fn, Okay, so Fn is our apparent weight. So make Fn as the subject. So it become Fg minus Fc. Fg minus Fc. Okay. Now look at this formula. Tell me, the Fn is your apparent weight. Fn is affected by centripetal force. Can you clearly see? Fn is affected by the centripetal force. Okay, now I give you Fn going to change if the centripetal force change, right? Okay, centripetal force got two formula, right? Recall back, mr omega squared, mv squared over r, correct? Okay, now let me see how many of you can really think well. Referring to this formula, tell me, Earth is now rotating with the speed of the day we calculated is like 5 times of speed of Formula One car around 1,500 meter per second, right? The speed the Earth is rotating currently. Okay, so the gravity yield at the edge is found to be 9.81 meter per second squared. Okay, how do you get this 9.81? We find the Fn divided by your mass. The G they got is 9.81, you know, from the apparent weight. Okay, now tell me, if the Earth, something cosmologically, some effect happens to the Earth suddenly stop rotating. Suddenly stop rotating. If the Earth suddenly stop rotating, you are standing on the wing scale. What will happen to the reading on the wing scale? Will increase? Will decrease? What do you think? The weight, the reading on the wing scale will increase or decrease if the Earth stop rotating? Answer me again through WhatsApp. Will increase or decrease when Earth suddenly stop rotating? You will get heavier or you get lighter? Okay, two of you say decreases. Think carefully. Look at the equation. Earth stop rotating. What happened to the gravity? If gravity decreases means normal force decreases, right? Normal force decreases. Therefore, that's why equating mg you get gravity small. So when Earth stop rotating, what will happen to the gravity? Is it decreases? Okay, two say decreases, one said heavier. You get heavier. The others, I give you 1 minute. Think. Earth stop rotating. What will happen? Yeah, three of you say increases. Should increases or decreases? Oh, everything is from this formula. Okay. So Fn equals to Fg minus Fc. Because if Earth stop rotating, if Earth stops, what happened to the Fc? Fc will turn to become 0, right? Fc becomes 0, no Fc anymore, no centripetal force anymore. The mr omega squared, omega is not anymore, omega is 0 already, no radian, no, or mv squared over r, the v becomes 0, centripetal force becomes 0. When centripetal force, which certainly has a certain value, but suddenly Fc drops, last time let's say Fg is 100, Fc is 10, so normal force you get 90. Okay, now what happened? Fg still 100, but Fc becomes 0. So normal force become what? It become 100. So normal force, when Fc drops, normal force rises, right? Normal force rises what? So normal force rises. When Fc drops, normal force rises. So when normal force rises, means you get heavier. You get heavier because normal force greater. Okay, the wing scale experience a greater force. That's why the reactions get big. Okay, you push harder to the wing scale. That's why the reaction get big. So you get heavier. So when you get heavier, the gravity tend to look like greater. You have a greater gravity. You feel like gravity getting stronger. This is the effect, the rotational effect. Okay, rotational effect causes effects the normal force. Normal force effect, which is the apparent weight, will affect the apparent gravity, the gravity we feel. Okay, so the gravity will be affected due to rotation. If the Earth stop rotating, the gravity will increase. Okay, the apparent gravity will increase. We feel heavier. Okay, this 1 year they asked this flow for 8 marks question. You know, it's like one complete structure 1 year came out. Part A, they asked you to draw the free body diagram. No gravity inside, normal force outside, 1 mark. Part B, they asked to write the, is it act upon by a balanced force and unbalanced force. Part C, they asked you to write the equation. What equals to the, can you write the, what equals to Fc? Part D, they asked, okay, what happened when the Earth stopped rotating? What happened to the gravity? So like one structured question they built up. Yeah, if I give you 1 minute, you can take down this. for this understanding. Anyone don't understand any part? Okay, so rotation affects gravity. Okay, rotation of the Earth affects gravity. Okay, now I'll give you 1 minute. Try to digest this. Okay. Now, the second factor affects gravity is the latitude. Okay, latitude, right? I told you latitude last time. Why latitude affects? Because the radius of the Earth is found to be a little longer than the North Pole, right? That's one reason. But there is another one reason why latitude affects gravity. Still connected to the rotation. Anyone can use this formula to explain why latitude affects gravity now? Can you give another reason in linking rotation? How rotation can affect latitude as a factor that affects gravity? You see, if you are close to the North Pole here, you see the rotate you are circulating also, but the radius of the circle you make close to the North Pole is shorter or longer compared to the equator. Equator you make a big radius. When you go to the close to the North Pole, the R get smaller. The R gets smaller. When close to the latitude, close to the North Pole, the R gets smaller. So can you explain now how rotation, how latitude affects the gravity? Based on this formula again, right? When you go close to the North Pole, what happened to the centripetal force? What happened to the centripetal force when you go to the North Pole, close to the North Pole? You are still circulating, but small radius. So what happened to the centripetal force? It's getting smaller or bigger? It's getting smaller, right? Getting smaller, right? Okay, what I'm doing. So here you get smaller, here the big radius. So if you stand here, the same thing. The normal force is equals to Fg minus Fc. Okay, so when you close to the North Pole, the Fc reduces. Why Fc reduces? Because mr omega squared, m constant, omega constant. Omega is constant. For the equator and then close to the North Pole, omega both of you constant because you have the same period 24 hours. So omega will be the same. So R shorter, so Fc shorter. When Fc shorter, the normal force increases. Normal force increases. When the normal force increases, normal force equals to mg, so g will increase too. Okay, so gravity gets stronger when close to North Pole. So latitude affects gravity. Latitude affects gravity. Latitude, how it affects gravity? This is another reason to explain. Because why latitude affects gravity? Because normal force equals to Fg minus Fc. Close to higher latitude, Fc is small, so Fn is greater, so greater gravity. This is the second way of explaining latitude effect. How latitude affects gravity. Okay. But in exam, the first effect is what? How latitude affects gravity. First explanation, they said different radius. They said different radius. Ellipsoidal. Okay. But in mark scheme, in the Cambridge mark scheme, looks like Cambridge prefer the second reasoning. Okay. Cambridge prefer the second reasoning. How latitude affects gravity.
Sir,
Yep.
why is centripetal force lower at high latitude?
Because centripetal force is mr omega squared, right? Mr omega squared. Mass, the same person is moving to the higher latitude, so mass constant. Omega also constant. Omega constant, right? If you are at the equator or you close to the North Pole, your omega is constant. What? So omega is what? Is 2 pi over a period. You still experience the same 24 hours when you go one round, right? At the equator or at the close to the North Pole. So period constant, omega is constant. So when you go close to the North Pole, close to the upper, what happened to the radius? compared to at the equator. Equator is a greater radius one. When you get closer to the North Pole, the radius get smaller and smaller. So you make a smaller circle, So when R gets smaller, what happened to the centripetal force? mR omega squared. R smaller, Fc smaller one. When Fc smaller, you will experience a greater normal force. Okay, experience a greater normal force. So that means you are getting heavier. So the gravity increases. Okay, Riyad, you got the idea?
Yeah.
Okay. So in exam, if they ask how latitude affects gravity, you just show this equation: Fn equals to Fg minus Fc. So at close to latitude, at close to the North Pole, the Fc decreases because it's proportional to R, smaller R, close to North Pole. So Fn greater, so greater gravity. Okay. So anybody, any other questions about understanding how gravity affected by these three factors? Altitude, latitude, rotation. Okay. Any questions? Okay, so I hope you understand. Okay, so we go to the PowerPoint. Okay, the Earth rotation. The Earth rotates about a polar axis, and its mass on the surface of the Earth rotates in a circle, decreasing radius for the equator to the pole. So the radius is decreasing from equator to the pole. G is minimum at the equator, where the centripetal effect are the greatest. Fc is highest at the equator. Okay, G is maximum at the poles, where the centripetal effect are not felt, because R gets small, Fc is small. Okay, that's why G has been altered. G has been altered. Okay. Okay. So yes, this is the part we discussed. So this is the electric gravitation field strength. So this is the graph just now we discussed. So remember, the factor affecting surface is altitude, depth, latitude, rotation of the Earth. Okay. Okay. So again, any questions before we proceed to satellite? How satellite is launched? Okay. No questions?
Just now the one about latitude. For centripetal force, why can't we use the equation mv squared over r?
Okay, good question. Why you can't use mv squared over r? Fc equals to mv squared over r. Why not latitude we use mv squared over r? Anybody can give me the answer. Why you can't use mv squared over r? Because if you use mv squared over r, we are checking what happened to Fc with a change in R, right? A change in R. So you are comparing, if R changed, what happened to Fc? The other quantity must remain constant, right? When you're comparing Fc with R. But mass is constant. Is it V constant? Is it V constant when you go from equator to the North Pole? V, the speed you are traveling. The speed you are traveling at the equator and the close to North Pole, the speed you are traveling, is it same or different? How do you find speed? How do you find V? V equals to R omega, right? R omega, right? So V depend to the R, right? So smaller R will have a smaller V. So V is changing. V is changing with latitude. So you can't compare R with Fc, Okay, when R change, V also changing. Okay, so that's why you can't use this formula. Because there is another unknown is changing. Okay, that's science, right? F equals to ma. How do you get the relation between how force linked with the acceleration? You must keep the mass constant, right? Then only you can see the relation between F and A1. That's why mv squared over r cannot be used, because when r change, not only Fc change, V change, speed change. When go up, V becomes smaller. Okay, Ashley, got the idea?
Yeah.
Okay, good. Okay, guys. Okay, guys. Okay, so now Next, we're going to talk about how satellite is launched. How satellite is launched. But before that, okay. Look at the first question. Just warm up first. Okay. Okay. Try to do the first question for me. Use the knowledge you learned so far. Give me the answer for the first question. Do you get 250? 1 minute for you. Like warm up first. Okay, what formula do you use to find for number 1? The gravitational force on a mass of 1 kilogram at the Earth's surface is 10 Newton. Assuming the Earth is sphere of R, calculate the gravitational force on a satellite on the mass 100 kilogram in a circular orbit of radius of 2r from the center of the Earth. Do you get 250? What formula do you use? So how do you get 10 Newton? 10 Newton is gravitational force of 1 kilogram. Earth, you have 1 kilogram. What is the gravitational force? What is the gravitational force formula? G mm over r squared should be 10 Newton. Okay, 10 Newton. Okay. So mass is 1 kilogram. Mass is 1 kilogram. That means gm over r squared is found to be 10. Can be 10. Okay, next. Same Earth, but the mass of satellite now is 100 kilogram. Is 2r. So what is the force? Gm, but it's 100. 100 over 2r squared. Just substitution. Substitution. So what happened? I do here continuously. So F equals to Gm over 4r squared times 100. So Gm r squared, this is times 25 because 100 divided by 4. Okay, so that's it. So Gm over r squared times 25. Gm over r squared is found to be 10. So 10 times 25, so 250 Newton. Okay. So first question. Okay, this kind of question is going to be very common. Like this double, what happened to the value? Okay, it's very common. Okay, any questions? So hope everyone get 250. Okay.
So can you repeat the explanation one more time? I kind of not follow.
Okay, because the first they said the gravitational force on a 1 kilogram mass. You have a 1 kilogram mass, and from the Earth's surface, the distance is r. They said the force is 10 Newton. They said force is 10 Newton. So what formula must come to your mind? Force between two masses. Gmm over r squared. The first formula introduced this topic. Force between two masses is Gmm over r squared. So according to the first data, Gmm over r squared should be equals to 10 Newton. Okay. So the small mass is the test mass last 1 kilogram. So you put small mass as 1. So it's found to be gm over r squared is found to be 10. Okay, that's the first story. Gm over r squared is 10. Okay, now they are saying the second story here, down here. Now got satellite of 100 kilogram is 2r away from the center. How much is the force on that satellite? So force again comes to gmm over r squared. But now the mass of the satellite is 100, so we put 100. And the r is 2r, so if we put 2r squared. Okay, so you expand, you get gm over r squared times 25. You don't know the mass, you don't know the r squared, but you know gm over r squared is what? Gm over r squared is actually 10. So we put 10 times 225, so you got 250 Newton. So the weight of the satellite must be 250 Newton. Okay. Who asked just now the question?
Me, sir. Farhan.
Okay. Can I get the idea?
Yes, yes.
Okay, so we go to the, I hope everyone no problem. So today we go to the important discussion, the application. So now what is the use of this Newton's law of gravitation? How to launch a satellite? Okay, when you want to launch a satellite, the two things you critically need to know is what height to launch and what orbital speed is required. These two we're going to calculate now. Okay, from Newton's idea, which is F equals to gmm over r squared. From this formula, we're going to get these two values. Okay, first, when you want to launch a satellite, when someone want to launch a satellite, they can't launch at any height you like. There is a specific height. Okay, the specific height we prefer is the height prefer so that it will have a period of 24 hours. Okay, we want a satellite. Most of the satellite we have in our world all are geostationary satellite, called geostationary satellite. Okay, geostationary satellite, later in the PowerPoint you'll get that term, which has a period of 24 hours. So we need to meet a satellite with a 24 hours, so that if Malaysia launched the satellite, so that the satellite is always above Malaysia, so that continuous communication throughout every day. Okay, when the satellite is when Malaysia is at this location, the satellite also above Malaysia. So continuous communication is possible. So for that to happen, the satellite also must have a period of 24 hours, because Earth also moving with 24 hours. Okay, so to have a satellite with period of 24 hours, you can't launch at any height you like. There is a specific height. So how to get this height? Okay, that's our discussion. How to get this height? How Newton helped to find that height? Okay, how to get that height? Okay, so the height calculated by using that, if the satellite is moving around the Earth, okay, what force acting on the satellite? What force acting on the satellite? The only force acting on the satellite is the gravitational force. Okay, so can you tell the satellite act upon by a balanced force or unbalanced force? It's act upon by a unbalanced force because it's moved in a circular path. Okay, so Fg equals to Fc. Okay, from here we get the height. Okay, Fg equals to Fc, right? The centripetal force of the satellite must be equal to the gravitational force of the satellite and the gravitational force of the satellite. Okay, so here, what is Fg? What is Fg between the satellite and this is Earth, capital mass, this is the satellite, small mass. So what is the gravitational force of the satellite? G m over r squared. This r is what? From the center to center of the satellite. This is the r. Okay, r. Okay, is equals to centripetal force of the satellite. So centripetal force is mr omega squared. Okay, so mr omega squared. The r is r, omega is the what do you call the angular velocity of the satellite. Okay, angular velocity satellite. Okay, this will, we want to get the height. Actually, we want to get the height, what height to be launched. Okay, so here from here gmm over r squared mr omega. Omega, if you put in terms of period, will be what? What is omega? Omega is 2 pi over t, right? So we put omega is 2 pi over t here. So what happened? So what happened? Equate. So this is mass cancel. So gm over r squared. You're going to be expand the 4 pi squared t squared r. So you rearrange t squared, you'll get this formula 4 pi squared gm r cube. Okay, get this unique formula. Okay, t squared equals to 4 pi squared over gm multiplied by r cube. Okay, this is the unique formula which really helps us to find what height to launch a satellite. Okay, how to know? Because what period do you want? What period do you want? Period you want is 24 hours. So the scientists use this formula. They put period key in 24 hours in seconds. That means multiply by 24 times 60 times 60. Okay. Then they need mass. This is which mass? Which mass is surviving? The mass of the Earth or the mass of the satellite surviving? Which mass cancelling? Which mass is cancelled? The mass of the satellite has been cancelled. Which mass is surviving? The mass of the Earth is surviving. So they put the mass of the Earth here. They find the R. The R they obtain, they minus with the radius of the Earth. They get the height where need to launch the satellite. So for this Earth, from the surface of the height h, if they launch the satellite eventually will have a period of 24 hours. Okay, if who's correct? This is only correct if gmm of r squared is correct. If Newton give the correct formula, and this should be the final outcome. So if they launch that height, it should give a period of 24 hours. So they launch it, it works. That means what Newton said is correct. The gravitation force is gmm over r squared. Okay, this is the proven. This is the application of Newton's law. Okay. So this is the first derivation explaining what height to launch a satellite so that we get a period of 24 hours. In exam, sometimes they'll ask you to derive this formula, 2 marks question. Okay, so you can memorize it, but in exam, you have to derive it normally. So how to derive it? Fg equals to Fc. Fg equals to Fc. Fc we use mr omega squared. Omega halfway we substitute 2 pi over t. We get this formula. It's a very important formula. Tells us what height to launch. Okay. This is in your PowerPoint. Okay, in your Word file also we have this equation. Okay, if I go to that equation here, scroll up. Okay, the derivations here. Yes, after the altitude, latitude, rotation. Yeah, so we have that derivation. This is the equation just now I showed you. Okay, so motion of moon around the Earth. If you go moon and Earth, then this is going to be mass of the moon. Mass of the moon cancel. So this is the equation. But this formula also applicable for Earth and satellite. If it's a satellite, this formula also applied. The mass of the satellite cancel. You still get back this formula. So this formula yields what height to be launched. Okay. Any questions, guys, so far? Okay. So that's why Newton contribute a very important thing to us, launching satellite, because it tells us what height to be launched with this equation gmm over r squared. Okay, so until now the satellite once launched, it works continuously without any problem. That means what Newton says looks quite what do you call looks correct. Gmm over r squared. Okay, so time's up. The next class we talk about what speed to be launched. That's another problem. They know the height now, but what speed to be launched. That's they got this equation. This is called orbital speed. Okay, next class we discuss about the orbital speed. Orbital speed. Any questions, guys, for today's lesson? So what you learned today? Learn about how gravity affect altitude, latitude, rotation, and what height to be launched a satellite with a period of 24 hours. We discussed that. Okay, next class we discuss about orbital speed. Any questions? Okay, no questions. Then we stop here today. Thanks.
Thanks.